Hey class, welcome back to Biology 9. This is the scientific method. Be sure to download your lecture guide at edmodo.com. Okay, so what is the scientific method? A scientific method is a logical procedure for choosing an answer to a question using deductive reasoning. Now, we've talked about scientists throughout history, and they're doing lots of different experiments and contributing their knowledge to the world. But the scientific community at large decided that they needed a method to ensure that the science that was coming in that the information gained by those experiments was gained in a correct manner, and that they were using a logical method to maintain the integrity of their experiments. So they decided on this kind of method. This required steps that all scientists would have to follow and prove that they followed in order for the scientific community to accept their work. So if you want to be in science, you're going to have to follow these steps all through college. For your doctorate, when you write your big papers, you'll go before a board and defend all of your work. So it's important to know the scientific method. You guys will need to use it in class when we go through labs and things like that. So it's really, really important, and it uses deductive reasoning. And just to recap from last session, deductive reasoning begins with several conclusions and draws particulars from them. So all men are mortal. Socrates is a man, so Socrates must be immortal. So the steps to the scientific method. The first thing we're going to have to do is define a problem. You have to have something, a clear scope of the type of question you want to answer. It must be limited so that it can be dealt with conveniently. It would be great if we could do one experiment and explain 10 problems, but it's just not possible. So you need to limit your questions and be very specific. As you guys are designing experiments in my class, I'll make sure to narrow your topic, and I will ask you to narrow your question and what you're going to be experimenting on. You're going to need to do some preliminary research to become familiar with the topic and make sure that nobody else has already answered your question. It wouldn't be a good use of time for you to reinvent a wheel whenever they are commonly in use. Okay, form a hypothesis, which is an educated guess, which attempts to answer the problem. So if the question I want answered is, will my neighbor hit me if I kick them in the shin under the table? My hypothesis would be, I think my neighbor would hit me if I kicked them in the shin under the table. So that's going to be my educated guess, just because maybe in the past, if I kick somebody, they hit me back, or that if violence begets violence, all of that. So that would be my conclusion or my hypothesis, and hopefully my conclusion would support that hypothesis. Then I would determine whether I should use a survey or experiment. Well, I definitely need to set up an experiment and control all the variables. If I'm also talking annoyingly to my neighbor while I'm kicking them in the shin, I wouldn't be able to tell which action caused them to kick me. So I'll need to set up an experiment to make sure I can get accurate data. The next thing, I'm going to have to observe the experiment or survey carefully and make sure that I set it up correctly. I'm going to start collecting information and recording it accurately. I'm going to make sure that I kick with the same kind of force and in the same spot and with the same participant over and over again, and see if the person kicks me or hits me back, how hard they hit me, where they hit me, if they're gaining pressure every time they have to hit me an additional time. All those things, I'm going to have to record that data, collect it carefully. I'm going to classify the data into logical groups. So if I hit female neighbors or male neighbors, maybe I can put those in two different groups. Analyze the data to determine what it reveals about the problem. Then I'm going to choose the answer that best answers my original question. Yes, when I kicked my neighbor under the table, I was hit repeatedly in the arm, usually once. If they were really annoyed, every fifth time I'd kick them, they'd hit me 3 times in the arm, things like that. Verify the answer by repeating the experiment. I would have to set up a similar experiment and do the experiment over and over and over again. Now, kicking my neighbor is not actually a good science experiment because scientists need to not do harm to their subjects. They can't inflict harm at any time. So I guess I'll have to think of another question to get answered in a real experiment. Okay, ideal experiments are controlled experiments. They've got basically two groups with only one different, with the only difference being the single factor that changes. So I would have to have another person sitting there in the same circumstances and prove that they're not hitting me anyway. Maybe it's just the way I look that causes someone to hit me. So I'd have the person I was kicking and then a person there that I was not kicking. and to make sure it wasn't just hit your neighbor day and I didn't know about it. Experimental versus control groups. The group that's not exposed to the variable is a control group. So the person I'm not kicking is the control. It's just someone to compare with. The person I am kicking is the experimental group. So they're the one exposed to the variable. Ideal experiments only deal with one variable at a time in order to conclude that the variable is causing the changes between the experimental and control groups. Okay? The variable has to be the one causing the change. So if you have a control group and experimental group, review which one gets the variable. Right, the experimental group. I feel like Dora the Explorer, like answering my own questions on here because you're not in class in front of me. Okay, the limits of science. Science deals with physical phenomena. Okay, experiments must be observable and measurable. We have to be able to see it and we have to be able to measure it for it to be in the scope of science. It's usually answered with a yes or no or a number. Questions using why or how are not measurable and therefore beyond the scope of science. The scientific method cannot explain phenomena. It can't explain miracles. It can't explain things happening simultaneously in the whole universe. We just don't know. So we have to be able to see it and measure it for it to really apply to science. Some limits of science based on this are that it has to be observable and measurable. Excuse me. Science can only describe what it's seeing. It can't explain it. It can't give it a value. No experiment can be completely controlled. There's always going to be gravity if we're doing an experiment on Earth. If we're doing an experiment on the moon, there's going to be gravity. The sun is going to have to, the sun will be exerting gravity somewhere. Even if we go into a vacuum, there's other factors affecting what we're seeing, and so we can't completely control an experiment, but we can try. Observations may be faulty. We may not be seeing what's really happening. Man's beliefs affect their judgment. Basically, we're biased, and a lot of scientists today, you could definitely say that they're biased because scientists, to make a living, they're being funded by people who need answers to their problems. So they're going to want to say, yes, this method of treatment of acne is working, and I believe it's going to work, and I'm seeing results on my acne-ridden mice or whatever my my experimental group that I'm doing because they need the money or they really believe in a product, so they're going to believe that it's working. So basically, our beliefs always come into play. Science must deal with repeatable results. You have to be able to do an experiment over and over again to prove anything. So if it's happening like a one-time event, if you're doing an experiment on Halley's Comet, you're going to have trouble proving things because it only comes by, once in a generation. So it might be hard to see it twice and control that repeatably. Science can't deal with values or morals. Science should not deal with values or morals. Now, this is a line that is overstepped a lot because science really appeals to people. They want to be able to take science and make a moral out of it, but that's not its role. Science can't prove or disprove a universal statement, and I'll ask you that why, and I'd like for you to answer it in your head and on your paper and turn it into me. And science cannot establish truth. Again, we talked about what truth is. We decided that truth is what is established in the Word of God, not what scientists decide it is. Okay, workable. This is just a vocabulary word that means that information, if we gain it by the scientific method, it's considered workable if it can be used in other circumstances. Workable is something that's contributing to society in some way because we can use that information. This is just a reminder about John Baptist von Helmont's experiment where he put rice. This is rice. I've heard wheat as well. Maybe he didn't record what his experiment was very well because there's some translation there. He put rice in a sweaty shirt into a box and he found mice and assumed that spontaneous generation had occurred. He didn't think that the mice could have been gnawing in from the outside or that they might have dropped in from above or who knows how those mice got in. They could have just clambered into the box. So he didn't control that very well. This was an example of really early science where they didn't have the method, and so it was easy to make mistakes in the outcome or the conclusions that was drawn from that one experiment. Francisco Redi, he was the one that disproved spontaneous generation. He did that by putting fish, veal, eels, and snakes into 8 different jars, and he put paper over some, left others open, and as the material rotted, maggots would appear in the jars that were not covered, and so he was able to disprove spontaneous generation and say that they had to have been contaminated by the flies. We watched a video in the last lecture about that. Um, but in this is not even a really good experiment because he's got too many variables here. You've got all these different types of meats in the jar. Some have paper, some don't, so the control is a little convoluted. Still, he was able to prove things without perfect scientific method, but that would be helpful. Okay, and then a wrong way to look at science is to believe that science is anti-God. Science is not anti-God. We are looking for ways to explain God's creativity, His creation, and it's great to look at science for those things. Um, Science is not anti-God. The Bible is true, and science is going to catch up. Science is the discovering of usable information about God's creation. So again, it's good. So science is not inherently bad. What we do with science can be bad. Pure versus applied science, again, more vocabulary. Pure science is where research scientists seek to find answers to questions. So there's just questions out there in the universe, and they're using the scientific method to go through and find answers to those questions. Applied science is, for example, a technician using methods that have been prescribed to him to determine something about a specific problem. So they're starting with a problem and trying to use previous science to answer that question. Pure science is kind of on the fringes. A good example of that is SETI, which is the SETI, which is a search for extraterrestrial intelligence. So it's like looking for life outside of Earth. Um, some people think that that's a waste of money, and maybe they're right. But that's pure science. I mean, there's no clear need for that, but some scientists believe that you need to just do science to be gaining information all the time without a specific purpose. Applied science might be, in the cure for, like looking for a cure for cancer. You've got this really specific problem, and you're going to use the scientific method over and over again, or use methods that have been prescribed to find a cure for cancer. Okay, it's not just looking at cells for the sake of looking at cells and getting knowledge. So why can man not prove a universal statement like we talked about before? Because it's an absolute type of statement. Every situation or area of the world, or the universe in general, it's not just the world, would have to be checked at the same time to determine the absoluteness of the statements. So you basically have to control the whole universe at once to prove a universal statement, and that's not a task that can be performed by humans. So it's kind of a ridiculous assumption that science could prove a universal statement. So that's the end of this lecture. Be sure to go through and answer those questions as well as you can. We'll be working on them together in class, so there's not a huge amount of pressure. But just know that you'll be required to apply the scientific method. You'll also be required in class to be able to recognize the steps of the scientific method in some examples of experiments that I'm going to show you. We're going to go through some Mythbusters and other types of experiments, and you guys will be able to pick out the different steps of the scientific method in that. So good luck, and don't forget to read. Reading is very important.